Greetings everyone. Today I, Bhavesh, Bhavika and Disha are going to present a brief about Cauchy-Riemann equations, their derivations and their importance. In the field of complex analysis, or overall we can say mathematics, the Cauchy-Riemann equations, named after two scientists, Augustin Cauchy and Bernard Riemann, consist of a system of two partial differential equations, which together with certain continuity and differentiability criteria form a necessary and sufficient condition for a complex function to be complex differentiable. The Cauchy-Riemann equations are a pair of real valued functions of two real variables, u as a function of x and y and v as a function of x and y, in which the u is the real part and v is the imaginary part of the equation. Also, we take z equals to x plus I y. Now, what are Cauchy-Riemann equations? Equations that are known to be as partial differentiation of u with respect to x equal to partial differentiation of v with respect to y, and partial differentiation of u with respect to y and my negative of partial differentiation of v with respect to x. These equations are also known as necessary and sufficient condition for a function to be particularly analytic in a domain. If we need to find whether a function is analytic or not in that particular domain, we need to find that does that function satisfy the Cauchy-Riemann or CR equation criteria. The theorem states that the necessary condition for a function f of z, which consists of the real part u as a function of xy and iv as a function of xy, to be analytic in a domain D is that the domain u and v and d satisfy Cauchy-Riemann or CR equation. The derivation goes as we take f of z with limit delta z tends to 0, that is equal to f of z plus delta z minus f of z upon delta z. Let z be a function x plus iy, where x is the real part and iy is the imaginary part. Therefore, f of z becomes u plus iv, that is u as a function of xy and iv also as a function of xy. Then delta z equals to delta x plus I delta y, delta z plus delta z, z plus delta z equals to x plus iy plus delta x plus I delta y, which further equates as x plus delta x plus I into y plus delta y. Finally, we get f of z plus delta z equals to u of x plus delta x comma y plus delta y plus I v into x of delta x and y of delta y. Now we come towards the derivation of Cauchy-Riemann equation. We get function of z, f of z, with limits delta z tends to 0 as f of z plus delta z minus f of x upon delta z, which equates as limit of delta z tends to 0 u of x plus delta x comma y plus delta y plus I v of x plus delta x and y plus delta y minus u of x comma y plus I into v of x comma y whole upon delta z. We further get limit delta z tends to 0 u of x plus delta x and y of delta y minus u of x comma y plus the imaginary part I into v of x plus delta x and y plus delta y minus v of x comma y whole equation divided by delta x plus I delta y. Now we have got the differentiation of delta z tends to 0 for the equation in both x and y axis. Now we have to separate it along the x axis as well as along the y axis. We take the case 1 along x axis, that is f of z limit tends, now limit becomes delta x tends to 0 u of x plus delta x comma y minus u of x comma y plus I into v of x plus delta x comma y minus v of xy upon delta x, which further equates x limit delta x tends to 0 u of x plus delta x comma y minus u of x comma y divided by delta x plus the imaginary part I limit tends to delta x tends to 0, v of x plus delta x comma y minus v of x comma y upon delta x. After further solving, we get f of x equal to deber u by deber x plus I into deber v by deber x. This gives us the first part of the equation, that is we name A. Now we come to the second part, that is along y-axis. F of z with limits tends to delta y equals tends to 0. We have u of delta x y plus delta y minus u of x comma y plus the imaginary part I into v x comma y plus delta y minus v x comma y upon whole I by delta y. This further equates x 1 upon I limit delta y tends to 0 u of x comma y plus delta y minus u of x comma y upon delta y plus limit delta y tends to 0 v of x comma y plus delta y minus v of x comma y whole by delta y. After solving further, we get f of z equals to 1 by I deber u by deber y plus deber v by deber y. We name this equation as equation B. Now we have got both the equations, one along the x-axis and one along the y-axis. We have given both the equations names A and B. Now we further equate equation A and equation B, and we get deber u by deber x plus I into deber v by deber x equals to 1 upon I deber u by deber y plus deber v by deber y, which further can be equated as deber u by deber x plus I upon deber v by deber x equals to minus I upon deber u by deber y plus deber v by deber y. After further comparison, we get deber u by deber x equals to deber u by deber y as our first equation, and deber u by deber y equals to minus of deber v by deber x as our second equation. Both these equations are collectively known as Cauchy-Riemann equations or CR equations. Now friends, we come for the polar form of the Cauchy-Riemann equations. We have f as a function of z equals to u as a function of r and theta, and f v as a function of r and theta, where u, that is the radial coordinate, equals to 1 by r v theta and u theta equals to minus r v r. And we have deber u by deber r equals to 1 by r deber v by deber theta, and deber v by deber r equals to minus 1 by r deber u by deber theta. Now let's take an example and further discuss the Cauchy-Riemann equations. We have the example taken as e to the power x plus iy equals to e to the power x cos y plus I sin y. We have u x comma y equals to e to the power x cos y, and we have another separated function v as a function of x comma y equals to e to the power x sin y. Now we calculate deber x u, that is a function of x comma y, equals to e to the power x cos y equals to deber y v to the power deber y v as a function of xy, and we have deber y u as a function of xy equals to minus e to the power x sin y equals to deber x v as a function of xy. Now we would march forward towards the application of Cauchy-Riemann equations. Basically, what is the use of Cauchy-Riemann equations? For a function to be analytic in a particular domain, it should satisfy Cauchy-Riemann equations as its basic criteria. Analytic functions play an important role for solution of two-dimensional problems in mathematical physics. Complex variables are also a fundamental part of quantum mechanics as they appeared in wave equation. Complex numbers are used in real-life applications such as electricity as well as quadratic equations. Basically, when an equation satisfies the Cauchy-Riemann equations, or when a function satisfies Cauchy-Riemann equations in a particular D domain, we get to confirm that the equation is analytic, and hence a function is proven to be analytic if that function satisfies the Cauchy-Riemann equations or CR equations. Thank you so much, everyone. Greetings.